So hi everyone, my name is Seonhong Min and I am a second year PhD student from Seoul National University, and I will be presenting my recent work, Functional Bootstrapping for Packed Ciphertext via Homomorphic evaluation. And this is a joint work with Yongsu Song and Dongwon Lee. So let me first give a brief introduction to homomorphic encryption and FFV scheme and the bootstrapping for FFV scheme. So fully homomorphic encryption is, as everyone might know, it is an encryption scheme which enables an unlimited number of computations of encrypted data. So usually, the most of the FHE schemes are constructed from RLW problem. So from RLW problem, we can construct something called somewhat HE, SHE, and it is an encryption scheme which supports a limited number of multiplications of encrypted data. So as you can see, it only supports a limited number of multiplications. It is not FHE. Say, in the first construction of FHE in Gen 09, so the Gentry came up with a special kind of operation called the bootstrapping. So basically, bootstrapping is a homomorphic evaluation of decryption circuit. So it means that the message remains the same, but it introduces a new noise with some fixed size. So the main bottleneck of homomorphic computation comes from the bootstrapping. So let's introduce the FV scheme. So we have the base ring R, which is a quotient ring of integer polynomials over some mth cyclotomic polynomial phi mx. Then we have the secret key sk. Usually we use a ternary polynomial with small Hamming weight, and it is from the base ring. And then we have the message. For some plaintext modulus t, we have the message polynomial mu, which resides in the quotient polynomial r t, which is a quotient ring of R over TR. And then we have the ciphertext. It has a form of a tuple over the quotient ring RQ square. So for some ciphertext modulus Q. So to encrypt an FV ciphertext, we first sample A from uniform distribution of RQ and E from some small error distribution, and we set B equals minus A times SK, secret key, plus rounding of Q over T times mu plus E. And to decrypt, we can simply compute rounding over T over Q times B plus A times secret key. Then you can simply show that it decrypts as mu the original message. So the encoding strategy of FV scheme is to store the message in the most significant bit and noise in the LSB least significant bit. So usually we want to use a simple arithmetic for FV scheme, since if you want to encode just a single integer modulo t, then it is a waste of the ciphertext space if you just encode a single integer to the large ring. So let's say that you have a prime number p which does not divide the cyclotomic ring degree m. Then RP there is an isomorphism between RP and some direct product of some finite fields. So let's say that D is the multiplicative order of P modulo M. And let's say that K is phi M over D, where phi is the Euler-Phi function. Then each Fix has a degree D, and it is a monic irreducible polynomial. Then since we have the isomorphism between RP and some direct product of those finite fields, we can perform simple arithmetic over a vector of finite fields. But usually we encode only the constant term and use the ZP to the K arithmetic. But what if we want to use a more large plaintext space? Then we can use the Hensel's lifting lemma, and we have the isomorphism between R P to the S and a direct sum of some ring. Then we can use a simple arithmetic of a Z for some vector of integers modulo P to the S. And then we have a plaintext change operation. So in every context, if we have the message which is a multiple of P, then we can divide the message by P homomorphically. So it's like change of interpretation, because we can just simply change the plaintext modulus, and then we can see the ciphertext as some homomorphically divided by P. So we will use this operation in the bootstrapping of FV scheme. Now, finally, I want to remark the scale invariant property of FV scheme. So note that the message is stored in MSB. We can change the ciphertext modulus as much as we want, but still the message will remain in the MSB. So for example, let's say that we are given an encryption with ciphertext modulus Q, then you can change the ciphertext modulus Q to Q prime by multiplying Q prime over Q to the ciphertext and then rounding it, but it is still an encryption of mu, the original message. So as long as the rounding error does not interfere the message part, it decrypts as mu, the original message. Now, let me introduce the bootstrapping for FV scheme. So let's say that we have an input of city, then firstly we do the mode switch and dot product and subsum operation. So in the mode switch step, we change the ciphertext modulus to P to the R. So what we want to do is here is that we want to make the decryption circuit as compact as possible by changing the ciphertext modulus to a small ciphertext modulus. And then we generate encryption of the noisy encoding of mu, P to the R minus S times mu plus E, by computing by putting the ciphertext into the message part of new ciphertext. And then we need to embed the noise into the valid encoding space, because usually the error polynomial E is a random polynomial, so it may not be a valid encoding space. So recall that we only encode the message into the constant term of the finite field, but since E is random, the finite field may there is a high probability that the E will not go into a vector of constant terms. So we have to use the automorphisms to get rid of the redundant term of E and make it into some kind of valid encoding. Now we have the coefficient to slot steps. So in this step, we homomorphically move the coefficients of the plaintext to the slots. So see that the rounding error is added to the coefficients. We have to move the coefficient to homomorphically remove the noise using the digit during the digit extract step, which comes later. So this can be performed with homomorphic matrix multiplication. And then in digit extract step, we get rid of the noise part homomorphically, and it can be done with a number of polynomial evaluations and division by P. And then finally, in slots coef step, we homomorphically move the slots to the coefficients back so that we can generate the original encryption of mu x. So this also can be performed via a homomorphic matrix multiplication. So it was very long and very hard steps. So I will show some kind of concise table to make it more simpler. So let's say that we have the input ciphertext of mu(x), which is an encryption of message vector m. Then during the mode switch step, the coefficients are changed into p to the r minus s times mu plus e for some small noise polynomial e. And then during the coefficient float step, we generate an encryption of the coefficient vector of p to the r minus s times mu plus e. And then during the digit extract step, we get rid of the noise part e. And then finally, in the slot coef step, we move the original coefficient vector to coefficient from message. Now, finally, let's get into the details of the digit extraction step. So during the digit extraction step, we have to get rid of the lower r minus s digits homomorphically, but there is no polynomial directly compute this. So we have to utilize some homomorphic division to circumvent this problem. So in HS 18, the authors discovered that there exists a series of digit extraction polynomial. So it essentially extracts the last digit of the input. So since we have the LSB, we can subtract it to the original input, and using the homomorphic division by p, we can get rid of the LSB. So if you see the algorithm, so you first compute GRU, which is the rth digit extraction polynomial, then you can get the last digit extracted. And then you compute u minus GRU, and then the last digit is removed. So you can use the homomorphic division by p. You can get rid of the last digit. So you can repeat this procedure for r minus s times, then the bootstrapping is done. So in practice, there exists a depth optimization, but I won't get into so much detail in this presentation. Now, let's get into the details of our work. So in this work, we have two main contributions. The first one is homomorphic LUT relation from ZP to the R to ZP to the S. So as I said in the last slide, this is generally a hard task because there may not be a polynomial function for they may not have a polynomial representation for this LUT. So we devise a general evaluation method for arbitrary LUTs. And then we propose a functional bootstrapping pipeline for any RLW encryptions. So similar to TF-8 scheme, it can bootstrap any RLW ciphertext regardless the scheme. But since FV and CKKS are the most prominent and widely used schemes among all those schemes, so we will focus on FV and CKKS in this presentation. So firstly, I want to remark that we will use a slim mode bootstrapping. So in normal bootstrapping, digit extraction operates on coefficients, as I said earlier. So we have to use slim mode, which operates on the message to get rid of the noise part and evaluate LUT over the messages. So in slim mode, slots to coefficient comes first to move the message to the slots, and then we perform mode switch to add the additional rounding noise to the message part. And then we move the coefficients back to slots so that we have some noisy encoding of the message in the the slots. And then we perform digit extract. So using this pipeline, we have this following table. So firstly, we have slots to coefs, and we have mode switch, and you have coef slots, and we have eval-LUT. So the only difference to the slim mode bootstrapping is that we have eval-LUT step instead of digit extract. So during the eval-LUT step, we evaluate LUT of the slots. So for example, if we have the FV scheme ciphertext for the input ciphertext, then during the slots cleft, we have some plaintext of MX, which has messages on the coefficient. And then during the mode 2 step, we have a noisy encoding of MX polynomial. And then during the cleft slot step, we move the coefficients to the slots. And finally, during the evaluability step, we evaluate some function f to the messages while getting rid of the redundant noise terms. And for CKKS, it is quite similar. So during the slots cleft step, we move the messages to the coefficients. And during the mode 3 step, the scaling factor is changed to some smaller scaling factor, delta prime from delta. And then during the cleft slot step, we move the noisy encoding of the original message to the slots, and then we evaluate LT over the messages. Now, let's get into the details of our homomorphic LT evaluation method. Firstly, we will focus on the case from ZP to the R to ZP. So let's say that we are given an LTF. Then hopefully, if there exists a polynomial which evaluates this LT directly, then everything is fine. But problem is that there is no such polynomials for most of the case. For example, even digit extraction cannot be evaluated via a single polynomial evaluation. So our observation is that such an LTF can be written as a multivariate function of its digit of the input. Then, so for example, if we have the LTF, then we can find some multivariate function tilde f, which is equivalent to the original LTF. And then, since we are operating on the finite field ZP, tilde f always has a polynomial representation. So, since we know that tilde f has a polynomial representation, it is evaluating f is equivalent to evaluate such a multivariate polynomial tilde f. Say during digit extract step, since I said that each digit is extracted, so we can use those digits to evaluate tilde f, and finally we evaluate f. But the problem is that tilde f is of degree at most k times p minus 1 with p to the k terms. So computing such polynomial can be very cumbersome. So in this work, we provide a more optimized version of the LT evaluation. So we focus on the Heaviside function. So Heaviside function is the most basic form of the step function. It is basically an indicator function. So it outputs 0 if the input is smaller than b, or where b is some kind of bound, and outputs 1 if the input is bigger or equal than the bound b. So why did I choose the Heaviside function? The reason is that LT for FV to FV function bootstrapping has a form of step function. If you look at the graph on the right side, then you can see that the FV to FV LT has a form of some step function. So for example, if the input is 0, the input message is 0, then the noise encoding of 0, the value of the noise encoding of 0 vary from minus p to the r over 2 to p to the r over 2. So basically FV to FV LT has some kind of step function form. So it is very natural to look at the most easiest form of the step function family, the Heaviside function. So, firstly, we observe some recurrency relation. So, given this Heaviside function with bound B, you can define two Heaviside functions using those bound B. So let's say that the bound B can be written as br-1 dot 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 b0 in digit p expression. Then we can define these two Heaviside functions over the p to the r-1. So first one has the bound of b to the r-1 dot 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 b1 plus 1, and the second Heaviside function has the bound b2, which is br-1 dot 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 b1. Then we can construct the following recurrency relation. So the original Heaviside function can be written as some summation of multiplications between these new defined Heaviside functions and a univariate Heaviside function for U0. Then since that univariate function can be represented with a univariate polynomial of U0, you can compute those directly from U0. And then we can also represent the other multivariate Heaviside functions using the recurrency relation that is written at the top of this page. So we can use this recurrency relation to efficiently compute the Heaviside function. But in fact, those two defined new Heaviside functions can be represented with two identical LUTs. So we can further optimize the time complexity of this method. So it only requires 4r minus 4 univariate polynomial evaluations of degree p minus 1. So maybe it may be really hard to understand the method just looking at those slides. So I have the algorithm. So if you see the algorithm, we have the bound B as an input and encrypted messages U0 to UR-1. Then firstly, we assign those values to x0 and x1. Then you can just iteratively compute x0 and x1 by computing the linear evaluations of x0 and x1 and some univariate polynomial evaluations of each digit. Then we can successfully compute the original Heaviside function with this iterative method. So you can just simply check with a simple coding. So I will leave as a homework to you. And we will get into the more generalized case of step function evaluation. So basically, step function is a linear combination of Heaviside functions. So for example, we suppose that we have an LUTF which has k intervals. Then it can be written as a linear combination of k minus 1 Heaviside functions. So you can use that algorithm from the previous slide to compute those k minus 1 Heaviside functions, and you can simply compute the linear evaluation of those Heaviside functions. And also, I would like to remark that one can generalize the recurrence relation as long as the number of the intervals are smaller or equal than p. Now, let's generalize this homomorphic evaluation method. So from zp to the r to zp to the s. So given an LUTF from zp to the r to zp to the s, we can define SLUTs fi, which outputs ith digit of the original LUT. Then we know that f can be written as a linear combination of the lifting of those new LDTs FIs so we have to change the space from ZP to ZP to the R. So we can reconstruct the original LDT. So it remains to compute the lifting of FI axis. So in other words, we need a method to compute homomorphic lifting. So we came up with this homomorphic lifting method. So firstly, we scale the input ciphertext by 1 over p to the I minus 1. Then the new ciphertext CT prime is an encryption of m plus p times I, where I is some kind of random value. So we can just simply evaluate the digit extraction polynomial to extract the message from the LSB. Then it concludes the homomorphic lifting method. So one may ask that why does it not need coefficient slots or slots to coefficient as in bootstrapping? Because during the bootstrapping we also extract some values from the noise encoding. But the difference is that in this case the message is stored in the LSB, but in the bootstrapping the message is stored in the MSB. So in this case, it is very easy to extract the message, but in bootstrapping, the case is the opposite. But it is also noticeable that when I is large enough, then the depth consumption can be mitigated and optimized with the usage of coefficient slots and slots coefficient. So we will refer to this method to MHWW24, and you can use the method of low degree null polynomial to optimize the polynomial degree. Now, let us compare our method to the TF-H-like schemes. So, in the previous works, there was 3 major drawbacks. So, firstly, in TF-H scheme, they don't have any remaining multiplicative level. And also it does not support large plaintext modulus, and also it does not support any simmed arithmetic. There have been some works that wanted to use a simmed arithmetic. For example, there was this line of work, amortized TF-H. So basically you generate lots of monomials and then multiply to the test vector. But this case, it inherits the disadvantages of the TF-H scheme. So it can compute the simmed arithmetic, but it does not support large plaintext modulus, and also it does not have any remaining multiplicative level. And in amortized TF-H using FV and SKKS, which will recent line of work, they achieve the large plaintext modulus, but still it does not have a remaining multiplicative level. And then there was some other line of work which computed the TF-H style, more like AP style blind rotation. So basically they rotated the root of unity using the automorphisms, but it may have some remaining multiplicative level, but it does not really support large plaintext modulus since they require lots of multiplicative level to compute this property properly. So our work can achieve all these problems like remaining multiplicative level or large plaintext modulus and simmed arithmetic. And finally, before we conclude this presentation, I would like to remark on the bootstrapping complexity. So traditionally, traditional bootstrapping, there are 3 types of bootstrapping. So firstly, we have traditional bootstrapping, and secondly, we have general bootstrapping, and third, we have functional bootstrapping. So in traditional bootstrapping, we need to operate on the message itself. So we need an ephemeral message space during the bootstrapping, which can accommodate the delta m plus e. And the time complexity was it should be depth complexity. So please excuse me. And it is depth complexity. So the depth complexity becomes O log p to the r plus log 1 norm of s. But recently a new paradigm of bootstrapping was proposed, the general bootstrapping. The idea is that you can extract the message from the original ciphertext and you don't need to care about the size of the message. So in this case, you need a small size of the ephemeral message space, which can accommodate delta E1 plus E2, where E1 and E2 are some rounding error. So in this case, the time complexity becomes, the depth complexity becomes O log 1 norm of S, and S, where S is the secret key. And for functional bootstrapping, since we have to operate on the message itself, it should have the same time complexity, depth complexity to the traditional bootstrapping. So we have some classifications of existing works here. So we have the traditional bootstrapping and for BZV and FV, and in general bootstrapping for BZV FV, we have two recent work, KSS24 and MHGWW24, which drastically reduce the time complexity for the bootstrapping for large plaintext BFV and BZV. And we have the functional bootstrapping for FV and BZV, which is our work. And there are some other works, which is not really a BZV bootstrapping, but it is some kind of partial BZV and FV bootstrapping, LW23 and LW24. And for CKKS, we have also general bootstrapping, KPK plus 22, and it has functional bootstrapping BCKS24. It is it will be presented in it was presented in your crypt 24. So bootstrapping with CKKS, it's some kind of functional bootstrapping with CKKS. And finally, we have feel like schemes. Since it inheritedly support the functional bootstrapping, we don't have any traditional bootstrapping method except for AP14, and it has general bootstrapping method AD plus 21, and functional bootstrapping is basically every few like schemes, and then you have some other schemes which has some kind of other functionalities than just feel like schemes. So hopefully we can feel the other section in CKKS by introducing some kind of interesting ideas from other researchers. And yes, this concludes my presentation, and thank you for listening. Should you have any questions, please feel free to ask me. Thank you.